Welcome everyone to the second colloquium of the semester. We're happy to have Professor Cheol-Hyun who will speak on geometric models of simple Lie algebras via singularity theory. Professor Cho just recently became part of the POSTECH math department, and let's welcome him. I'll speak in English, not because I speak fluently, but we have many foreigners. Okay, so somehow this is a bit strange talk. I'm a symplectic geometer, and I'll speak about Lie algebras using singularity. So it's kind of intersection between three different things. But there will not be any symplectic geometry in this talk. So because it's kind of in the intersections, I'll give some very brief definitions in each field. And in the second part, so we are going to construct a kind of very nice looking thing, which we call Coxeter fields. And so we'll see how these dots arise from Lie algebra theory, also how this kind of polygonal shape arrives from geometry explained. And the third part is geometric root systems. So these root systems are kind of one of the most fundamental notions in Lie algebra theory. And we define what is called geometric root system. So this will be just these kind of diagonals in this field. So kind of very geometric object, but we'll using intersection numbers, and there's some kind of maps, kind of monodromy maps and so on, using, so we'll define kind of a pairing, and this will become isomorphic to the classical root system in the Lie theory. Finally, in number 4, we are going to kind of give a geometric definition of simple Lie algebras. Okay, so let me start with definitions of simple Lie algebras. Okay, so Lie algebra is nothing but a vector space with this operation called Lie bracket, which is an alternating bilinear map satisfying Jacobi identity. You all know this. And Lie algebra is called simple if it's non-abelian. It's called abelian if bracket is 0, and if it's non-abelian and it contains no non-zero proper ideals, something really simple. And the examples of simple Lie algebras will have this AN, DN, and E type. And AN, Lie algebra is given by this SL and C, which is the space of trace zero and by matrices of complex number entries. For example, SL3C is this 3 by 3 matrix whose trace is 0. So if it's diagonal, then you have this 1 and minus 1, and the trace is 0. If you have 1 and minus 1 here, and it's also trace 0, and you have nothing on the diagonal, then they all trace 0, right? So this E12 means at 1, 2 spot, you have 1 and 0 in everywhere else. So we have this 8 generators of vector space, and they are also quite important generators as Lie algebras. The Lie bracket is given by this commutator of these matrices. And Dn is a skew-symmetric matrices, SO2 and C. So it's a 2n by 2n matrix, which is skew-symmetric. And you can check that the Lie bracket of skew-symmetric matrices are again skew-symmetric. So it's a kind of a Lie algebra. And the E-type simple Lie algebras are difficult to describe, but they exist. So this E-type, there are 3 E-type Lie algebras, E6, E7, E8. Their dimensions are 78, 133, and 248. Okay, kind of big. All right, so So it's like more than 100 years ago. Simple Lie algebras are classified by Killing and Cartan. And in the process, they use the notion of Dinkin diagrams. So Dinkin diagrams are these kind of diagrams with vertices and edges between them. And so here, these sub-indices 6, 7, 8 are in fact the number of vertices in the diagram. So this E8 means there are 8 vertices. You can check there are 7 here and 1 here. So the theorem is that the simple Lie algebras given by this ADE family together with this another family, and this is called non-simply erased. Their Dinkin diagrams have kind of multiple edges and arrows. So we'll not talk about these non-simply erased ones. Let me just mention that these non-simply erased ones are least of algebras of simply erased ones. So somehow you can see them inside these ADE algebras. All right. So these ADE type Lie algebras the subject of this talk. So we want to kind of find a geometric model of this simple Lie algebras. So we need to know a little bit of the structure of these Lie algebras. So there is one of the most basic theorem of the Lie algebra is this Cartan decomposition. So given a semi-simple Lie algebra, we have a Cartan subalgebra H and direct sum of eigenspaces G alpha. So this H is a subalgebra whose bracket is 0. So the bracket is 0. And so now taking a bracket with H bracket of inside H is 0, but bracket of H with other vectors can be non-trivial. And so H acts on the other space. And so this Cartan subalgebra acts and it admits this simultaneous eigenspace decomposition. So we learned in linear algebra that when operators commute, then we have a simultaneous eigenspace, right? Because this bracket within H is 0. So somehow taking bracket in H decompose this space into eigenspaces. What I mean by eigenspaces, when you have this element of this Cartan subalgebra H, when you have this vector, G in this eigenspace G of alpha, then taking a bracket of H and G is again G, but whose eigenvalue is given by this function of H. Right? So this alpha is kind of eigenvalue function, and this eigenvalue function is called roots. And so alpha is a root, and this P is the set of roots. Okay, maybe maybe you have forgotten this, but anyway, so this is the Cartan subalgebra, just diagonal ones, and they act on here, and these are actually eigenvectors, common eigenvectors. You can take a bracket and check that they are eigenvectors. For example, so for the case of E12, if the bracket of H1 with E12, very convenient, yeah. It was another quiz. Twice of E12, and if you bracket of H2, then it's minus E12. So E12 is an eigenvector, and the eigenvalue E and minus 1, you can think of it as a linear functional on this Cartan subalgebra, right? Because it's 2 for H1 and minus 1 for H2. And because so for each Eij, we have a root. So we have 6 roots: E12, E13, E23, and E31, E32, E32, and so on. So we have 6 roots. So that's So we have two diagonal elements and six roots and one-dimensional eigenspaces for each root. So that's this SL3C. So two diagonal elements and six generators. Okay. Also, there is so-called Cartan-Kelling form, which is a non-degenerate bilinear form defined using this odd-joint representation. Let me skip this. But anyway, so in our case, this gives us some kind of inner product, non-degenerate inner product. So we have seen one root, and there are six roots, and so these are kind of representing the six roots for SL3C, and the properties of these roots are formalized as a notion of root system. Namely, these six roots can be put into a Euclidean space, satisfying certain axioms. It has a kind of symmetric structure. For example, you choose any root alpha, then you can define a reflection. So given an alpha, you look at the hyperplane perpendicular to alpha and define the reflection with respect to this hyperplane. Then you can see that. So if you can see that if you have alpha, then you take a perpendicular hyperplane, and the reflection somehow preserves these roots. And then these reflections generate what's called bi-group of the corresponding Lie algebra. Okay, so I think you probably have learned it from last semester. No. Okay. Anyway, so this kind of basic things. And again, one more thing. So there are two kind of simple bases of roots. So in this case, alpha and beta is the best basis, in the sense that all the other roots can be given as all the positive linear combination or negative linear combination of these two vectors. And vertices of the Euclidean diagram correspond to these basis vectors of the simple basis. Edges corresponds to some kind of angles between this simple base alpha and beta. So yeah. And the bio group has a distinguished element called Coxeter element, which is obtained by composition of reflections corresponding to simple root. In this case, maybe reflection with respect to alpha composed with reflection with respect to beta. So, yeah, that's composition of two vectors. And this is E8 root system. I told you that the Lie algebra is dimension 248. So the Cartan subalgebra is 8-dimensional. So the eigenspace is 240-dimensional. So there are 240 roots. And the picture, you're supposed to see 240 roots, but you cannot really see it. Right? So what this means is we have 8-dimensional space. So imagine 8-dimensional space, and we have 240 vertices in the 8-dimensional space. And you project to certain 2-dimensional plane. Then, so these dots, if you start counting, you have 30 dots on one circle. And you have 1 circle, 2 circles, 3, 4, 5, 6, 7, and 8 circles. So in total, you have 240 dots in this diagram. So they are like the projection of roots in the plane. Okay.
What does the color represent?
The color? I don't know. Sorry. So these edges are supposed to represent that the Lie bracket is not zero. In fact, also it represents that in 8-dimensional space, these vertices, you can think of the convex polytope, convex hull of these 240 vertices, and then you will have edges, right? And then it's the projection of edges are here. These are, So there is so it's 8-dimensional, but there is a very nice 2-dimensional subspace called Coxeter plane. This is where this Coxeter element kind of is a kind of this kind of elementary rotation in the plane. Okay. So anyway, so there is a notion of Cox's plane, and that's the most. And then you can imagine that in 8-dimensional space there are kind of many 2-dimensional subspaces, and the projection images could be very different if you choose a different subspace. And I guess we want the most kind of symmetric projection to 2-dimensional plane, and this is given by this Cox's plane. Okay, so we're going to construct a geometric model for this AD simple Lie algebras. This will be done in 2 steps. The first, this is a joint work with Wonbo Jung, who's a former student of mine, and Bumsuk Kim, who is here. And okay, so we'll do it in 2 steps. First, we define a geometric root system using curves on surfaces. The second, we define V bracket using intersection numbers between curves.
What do you mean by geometric model?
So this is okay. So suppose you don't know the definition of simple Lie algebras. So starting from geometry, you can define simple Lie algebras. Everything using so kind of you give a geometric criterion, and that defines some kind of special curves. There will be a generator of the vector space, and the bracket is defined by using certain intersection numbers. Yes. And as a small application, we can kind of realize this theorem of constant, which says that when you have a constant element, let's say H is the order of constant element. There is a famous theorem that constant elements X on the set of roots with n orbits. N is the number of vertices, and each containing H element. And we'll see a kind of graphical presentation of this. Okay, so what's the idea? So the idea is using singularity theory. So it's classically Arnold. So singularity is kind of this kind of functions, x cubed plus y to the fifth and so on. And Arnold classified in the 70s, classified singularities and found that the same Dinkin diagram as in this Lie algebras somehow classify simple singularities. So a singularity is called simple if its deformation contains finitely many isomorphism classes of singularities. So this is a bit difficult to accept, kind of understand, but you can imagine that its deformation means you add kind of small terms and then ask, if you add small terms, then your singularity is kind of changes into changed into different singularities, and it's called simple if these different singularities occur only in finite time. And
sorry, can you define what the singularity means?
Singularity just means that the derivatives are zero.
Singularity in what? In 2-dimensional combined space.
Maybe if you see the next picture, it'll be clear. So, but let me also mention that, so this is the classification for 2 variables. So an is x to the n plus 1 plus y squared. Dn is x to the n minus 1 plus xy squared. E6 is x cubed plus y to the 4th. E7 is this one, and E5 is this one. E8 is this one. And when you have 3 variables, just add z squared, and that's also the list of simple singularities. So how do we understand? What is singularity? This is what we mean. So when you have f, say x squared plus y squared, then you can think of it as a function from C2 to C, and you can check that the fiber at 1, the preimage of 1 is something smooth, preimage of 0 is something singular. So you have singularity here. You can check that the derivative at 0 somehow vanishes. So this is the singularity. And as you travel from 1 to 0, so this left circle is actually the real solution space. So if you think of x and y as real variables, then x squared plus y squared equal 1 is just a circle, right? And this circle shrinks and becomes a point. So this is what happens. So this circle shrinks to a point, and this circle is called vanishing cycle. And this, when so this singularity of this form is usually called Morse singularity of two variables. If it's one variable, it's just x squared. If it's three variables, just add z squared and so on. So you add those quadratic terms, then squares variables squared, then that's Morse singularity. So how about A2 singularity? Instead of x squared, you consider x cubed. So when you have x cubed, we kind of slightly perturb it so that we have x cubed minus x, let's say, slightly perturb it. Then if you look at the graph for real values, then this is x cubed graph. This is x cubed minus x graph of this. And you can check the maximum and minimum. So there is one critical point here, but somehow you have now one critical point split into two critical points, which locally looks like minus x squared and plus x squared, right? So this is usually called Morsification. So deforming complex singularity into more simpler ones is called Morsification. And now what are the vanishing cycles? So let's look at the preimage of this value. The preimage is like 3 points. And as you approach the critical value, so these 2 points somehow collapse. So this is a vanishing cycle. And as you approach another critical value, these 2 points collapse. So we have these 2 points are vanishing cycles, and these 2 points are vanishing cycles. So you have 2 vanishing cycles which intersect at 1 point. So that's kind of A2 Lincoln diagram. Okay. So instead of x cubed, let's look at x cubed plus y squared. Let's add one more variable. Then the Miller fiber is this x cubed plus y squared equal 1. This is a Riemann surface with boundary. And as you approach 0, some singularity appears at the origin. Okay. And so now this is too singular. So what we want to do is we want to kind of mortify it. So we mortify, and as before, we get 2 critical points. So these single critical points become 2 critical points. So as a mortification, we add x cubed minus epsilon x plus y squared. That's the. And then what we can do is from 1 you can go to this critical value. Then in the solution space, some circle somehow collapses to a point. So this is the vanishing cycle for this pass. And for the second pass, you have another vanishing cycle. And you can see that these 2 vanishing cycles intersect like this. So you have vanishing cycle 1, vanishing cycle 2, intersecting at a point. So that's Lincoln diagram. And in general, when you have kind of very singular critical point, you mortify and you have several critical values, and you choose kind of the passes from a regular value to a critical value. And this choice of paths define collection of vanishing cycles, and it's called distinguished collection of vanishing cycles.
Okay, how can you define intersection of 2 cycles here?
This is the real intersection. So you have this cycle here and this cycle here, so they intersect at 1 point. So it's a punctual torus. So you have meridian and longitude intersect at 1 point.
what if we choose other type of modification?
Right, you can choose other type of modification. You can choose, instead of this path, you can choose this path and so on.
Oh,
Yeah, then the vanishing cycle is changed. So this collection is not unique. There is a kind of choice of grade group acting. And it's known that other types of modification can be realized as a different choice of vanishing paths. You can just work with one modification, but choose different choice of vanishing. Okay. Now, another thing we need to know is this monodromy. So there is a regular value and there is singular value. Instead of going to the singularity, you can just walk around the singularity. And using the parallel transport, you can see what happens. And when you define parallel transport, you ask the parallel transport somehow to fix the boundary of this Miller fiber. And in the case of more singularity, it's known that when you have this vertical line, it's kind of then twist of this vertical line if you go around this singularity. Another well-known fact is that if this point is singular, then this map is always non-trivial. So that's another fact. If this map is trivial, then there is no singularity. That's another theory. Okay. And usually when you say monodromy, it's actually so it's going around this single critical value or going around all critical values. So that's what we are considering as monodromy. Okay. All right. There are two operations we need to know. One is the variation operator. So variation operator sends this kind of vertical line to like a closed curve. How do they do it? You look at the monodromy image of this vertical line and consider you look at the difference between two. So in this case, it's the difference of these two images. You can see that the difference of those two lines just a compact closed curve in the middle, which is the vanishing cycle in this case. So that's the variation operator. And there is a bilinear pairing, as in Lie algebra, Catan-Killing form. There is a so-called Seifert form. This is nothing but variation inverse of V1 intersect V2. So if you know topology, you know that the intersection number of these two arcs are not well defined because they have boundaries. But if you intersect an arc with a closed curve, then that's well defined, and that's kind of actually those two are Poincare duo. So this is instead of intersecting two closed curves, you can make one into open arc and take intersection. But it's well known that this variation operator is an isomorphism, so you don't lose any information when you take variation inverse. And this pairing is called Seifert form, and it's not degenerate. So this is a very good pairing. Any questions? Maybe.
Symmetric, right? Is it symmetric bilinear form?
It's not symmetric. This is not symmetric because you're taking variation of one thing and intersecting the other.
And is it alternating? Is it alternating one?
It's actually not alternating.
Just bilinear.
This is just the bilinear. Thank you for a nice question. Okay. So this was known. So for three variable AD singularity, the intersection form on the second homology of the Miller fiber, somehow, if you compute, you can compare it with Catan-Killing form on this Catan subalgebra. And there is what's called Picard-Lepton transformation, which is like taking a dentist with respect to certain sphere, vanishing sphere, and somehow the formula looks the same in this case, the reflection in bio group, and the vanishing cycles should correspond to roots. So this was like 70s. So this says that if you have three variable AD singularity, this intersection form, Picard-Lepton transformation, and vanishing cycles somehow define the root system. And from root system, it's known that there's a unique optimization simply algebra. So, but somehow this step is kind of loses geometry. So, and also this system itself is not very geometric. I mean, it's hard to visualize all these vanishing cycles actually. So what we are going to do is what we are going to do is we are going to give a formula for simply algebras using arcs. We are going to use arcs and monodromy, variation operator, and Seifert form, what I just introduced. We're just going to use all these three informations and define simply algebras. So this is our suggestion for SL2. So SL2 is a trace zero matrix. So you have three base generators, 1 minus 1, which is 0, and there's 0, 1, 0, 0, and 0, 0, minus 1, 0. So this is usually called SL2 triple. And what is the corresponding SL2 triple in A1 singularity? We're going to take it as this arc alpha and its orientation reversal, alpha bar, and its variation, the variation image of the variation operator, which is the difference of the monodromy image with alpha, which is discrete. So V alpha bar, which is somehow alpha, its orientation reversal and variation image is SL2 triple, and that's kind of what will hold generally, given, yeah. So this will be structure of SL2 triple for all simple algebras. And we need to actually understand how these interact with each other. Okay, so let me move on to Coxeter fields. Okay. Question?
Excuse me, you mean the simply algebra correspond to the curve on the mutant fiber, on the regular fiber?
So, but what I'm using is this is a regular fiber.
Yes.
And so this regular fiber has a homology class, which is this one. That's this one, and it has this distinguished kind of arc alpha. So I take this alpha and its orientation reverse alpha bar. And I'll define Lie bracket using intersection numbers later on. And that becomes isomorphic to SL2.
Yeah. I mean, in general, you consider similar thing on the regular fiber.
Right. So I consider regular fiber, but somehow it's related to this vanishing cycles and monodromies and so on. So now the singularity information is encoded in terms of in other data. Okay. So to find the geometric model, we need to define what is called Coxeter fields.
So can I ask one more?
Sure.
In the previous example, how can you prove that self-intersection number of alpha, self-intersection number of H is 0? How can you prove it?
Right. So we are not looking at the honest intersection numbers. The intersection numbers kind of combination. For example, we are going to look at intersection number of V of alpha and low alpha. So we have two intersections. So that's why the bracket of H and E has two. It's twice of E.
But since H is a generator of Cartan's algebra, so its self-intersection number should be 0.
Right.
So how can you prove that self-intersection number of V is 0?
Self-intersection number of V is indeed 0, so you can just move it upward. But we are not using that. We just anyway, so, but anyway, so we kind of cook up a formula, but we just take the brackets of these guys to be 0 by definition. But self-intersection numbers are 0 because you can just move it along. Okay. So in order to understand this Coxeter wheel, we need to better understand this Miller fiber. So AM Miller fiber is the solution space of this x to the n plus 1 plus y squared equal 1. So x and y are complex numbers. So you move x to the n plus 1 to the other side and take square root. And we learned in complex analysis that you can actually solve it, but there is ambiguity of plus minus 1. So to take the square root, we need to kind of take the branch cut. So inside the square root, there are 3 zeros. So you take a branch cut, and somehow the solution space is a 2-to-1 covering over this thing. So I just draw two coverings after branch cut, and then when you glue the bottom of this A with the top side and the upper side to the lower side, like this. And so just topologically somehow manipulate this thing into like this. So this is same as this one, where this infinity part become like a small r, and then you glue according to the rule of branch cut. Then this is what we get. So, and also you need to glue the opposite sides like this. And an exercise that if you glue opposite sides of a hexagon, you get torus, and there's a puncture. So it's a puncture torus in the case of A2 Miller fiber. So in the case of AM Miller fiber, you just have more cuts. So now it becomes bigger, but essentially it's the same. For DM Miller fiber, it's similar, but you need to divide by x. So there is another whole point and another branch cut. After doing similar thing, you realize that the Miller fiber can be given by this 2n minus 2 gon with opposite sides identified. So this you glue this with this with this, this with this, and this with this. So that's the solution space of that Miller fiber. And E8 for x cubed plus y to the fifth equal 1. We do it as before. So we have some kind of small triangle. Something like this. But we have 5 copies. We have 5 copies like this. And if you're not familiar, this is quite helpful. So the solution space admits Gmod 3 times Gmod 5 action, which is multiplying third root of unity to x and fifth root of unity to y. So third root of unity action is just rotating like this, and fifth root of unity is like rotating these legs. So this is the solution space. All right, and how do we make the Coxeter wheel? We are going to do a very strange thing somehow. I cannot explain easily why we do this, but this is, you'll see the result is actually very nice. So this is B1. So there is A4. I cut this Miller fiber into smaller triangles and pentagons. So there's 3 triangles and there's a pentagon. And these small pieces actually glue together to form another 2 pentagons. So this B23, B24, B25, B21, B22 move to a pentagon, and B33, B34, B35, these three forms, these 5 pieces form a pentagon too. And then we're going to cut these into pieces, and we're going to glue in the following way. So starting with A2, go to B1, A4, and this B34, B35, B31 triangle, the pentagon. And then A1, and another pentagon, and A, and so AB, 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 and like this. at the end, you get this nice necklace kind of thing. You can actually observe that this pentagons appear 3 times. So there's B1 here, there's B1 here, there's B1 over there. You can check that actually these are identified by Euclidean translation. Also B2 here, B2 here, there's B2 there, and you can check that they are also identified Euclidean translation. What this means is that the original Miller fiber actually had a kind of flat metric. But anyway, so this pieces actually appear several times. So this is kind of a covering space of our Miller fiber. And in fact, monodromy is very nice on this field. So what is monodromy? Monodromy is just go to the opposite side and just one click. So B3 will go to B1 over there. So, and this A5, wait. B3, oh no, sorry, B3 will go to B3 over there, and A5 will go to A3 over there, and so on. So you go to the opposite side and one click to the left. So that's kind of the monodromy of the singularity. All right. So what? So then we learned that actually this is very similar to these pictures arising in Lie theory. So if you Google Lie algebra, then you see kind of picture we have seen before. And if you just collect the dots, so these are the dots. So 280 dots, 240 dots in the case of E8. And if we found that actually this field can be put on the outer shell of this field as follows. So 30 dots here, and then but inside this you have to go like zigzag, like to have these pentagons and so on. Okay. So
the picture in the left-hand side means just the projection onto the
yes, this is the projection of the roots. Yes. And this is what we just made out of Miller fiber. And this is the case of E6, and that's the case of E7. Okay. All right, so what do we do with this Coxeter field? So we are going to look at all these kind of arcs, which are diagonals of like which called spokes of the field, or the edges of the field. So we want to so we saw that the Lie algebra has this Cartan decomposition. So in order to construct one from geometry, it's actually helpful to kind of have this duality in mind. So one is this H, the geometric Cartan subalgebra. We want to take it as just middle dimensional homology of the Miller fiber. So if it's puncture torus, then just these two curves, two circles in the middle. And by Poincare duality, the dual space as a vector space, you can identify it with this relative homology classes, which are classes of arcs. So these two are dual to each other by Poincare duality, but we're not going to use this Poincare duality. We are actually going to use this Seipert form to describe the duality. So anyway, so that will come later. But just keep in mind that these are closed curves. Somehow these are arcs. So open arcs, closed curves, and arcs. Okay, so that's the decomposition. And of course, when you have an arc, you can radiation image should land on the closed. It's a closed curve. So it actually lands here.
In the definition, so usually Cartan algebra is unique of the conjugation, but in this case, your geometric Cartan subalgebra seems to be canonical. Is it?
Right, so we haven't chosen the basis. Yeah. So, for example, if you choose a path, you get these vanishing cycles. And if you choose different paths, you get different vanishing cycles. They are all basis of this middle dimensional mode. Okay, so according to, so within the class of arcs, there are a kind of very distinguished one, which is called vanishing arc or geometric vanishing arc. So these are the ones whose variation image becomes a vanishing cycle. So if you have an arc, if you have a monodromy image, then the variation image is like a closed curve. There is no guarantee that this is actually a vanishing cycle. When it becomes vanishing cycle, so this arc will be called vanishing arc. And in recent paper with Bae, Chua, Jung, and Pablo, we kind of found one sufficient condition when genus is bigger than 5 to become a vanishing arc. But actually, this does not apply in our cases because genus is too high. Okay. But So we have seen that these somehow classical root system for A2 singularity, SL3 have these 6 vectors. For the geometric root system of A2 singularity, I told you that the A2 Miller fiber is this kind of hexagon with opposite side identified with puncture. This is a puncture torus. And the arcs that we are considering are these arcs and their orientation reversers. You can see that actually there are one-to-one correspondence, right? This upon alpha, the 3 kind of corresponds. You have these two, you have 6 vectors, and you have also 6 vectors there. But this is a coincidence. For A3 singularity in the plane, you have some kind of 4 punctures, and you have many diagonal arcs. But root system for A3 singularity, A3 will be in 3-dimensional space. It will not be in the plane. So if you just go to other root systems, they are in high-dimensional Euclidean space. But because we are looking at curve singularity, these arcs will be kind of 2-dimensional. So then you can immediately realize that we need a different metric or different geometric pairing, because in 8-dimensional Euclidean space, you have a nice pairing. But when you project to some 2-dimensional space, or if you go to different subspace, then your pairing is not good. So the pairing we are going to use this cycle form of the singularity. So what is the pairing? So the pairing is this one. So when you have given 2 arcs, so you look at variation of one arc intersect with the other one, or variation of the second arc intersect with the first one. So in a sense, this pairing is not symmetric. So we kind of symmetrize the pairing. This is symmetrized pairing. And we show that in fact, we can characterize vanishing arcs if and only if their length equal to 2. Okay, and for AD singularity, you can try to find the number of arcs, number of vanishing arcs, and it turns out that they actually agree. And we can actually show that these vanishing arcs form a root system and verify the axioms of root system. So how is it related to the classical field? So we know that there are, for example, 240 vanishing arcs for EH singularity, but what are they? We need to know the precise arcs, 240 arcs. We need to find the 240 arcs. And so that's where this Coxeter field will be used. So from the definition of Coxeter field, there is a projection map from Cox-Sector field to the Miller fiber, because we had this, we recall that we had like, when you have a pentagon, you have like 3 different copies of pentagon, right? So you can project to the Miller fiber where there is only 1 pentagon. So, and then we say that 2 arcs are equivalent if the projection image is the same in homology, in relative homology. So this is, so we define some equivalence classes among arcs in terms of relative homology in the actual Miller fiber. And then we show that actually geometric roots in one-to-one correspondence with equivalence class of edges and diagonals or spokes of the Cox-Sector fields. So this is the classification theory of roots. So we have the Cox-Sector field, and if you just look at edges or diagonals, then they are the roots, geometric roots. And when they are equivalent, then they define the same vectors. So that's also another result. So can you see 240 roots? So there are much more than 240 diagonals. But what happens is that this edge somehow appears something like 3 times. Is it right? 3 times? Or 5 times? I don't know. So usually, if this, I think in E8, all the edges that have the same length and parallel are actually equivalent. So this edge is in fact equivalent to this one, and equivalent to this one, and so on. So you can check with the ruler. You can check whether they have the same length or same direction. If you have a you can measure the angles. Anyway, so equivalence is not really something difficult. You can check because you know which ones are kind of identified and so on. Anyway, so these are 240 roots. So now we want to define the algebra. Anyway, do you have any questions?
Can I? So I was just a bit like confused. Like, so we're using arcs like one-dimensional object here.
Yes,
but
yes, please.
that like when we but like when we like do something like vanishing, so like consider something like vanishing cycles, like to consider like higher dimensional.
So this is for the 2 variable singularity. So the vanishing cycles are closed curves.
Yeah.
So if you want to imagine kind of 3 variable case, you have this one, and you have a kind of mono variation image, which is a closed curve, and you do the like this suspension, and you get a sphere. Something like that. But so the good thing about arcs is it's kind of easy to visualize, and you'll find that the re-bracket of arcs somehow is related to, so this arc with orientation, you can think of them as vectors, right? And then when you take re-bracket, you are going to add these vectors. It's kind of related to additional vectors. It's actually because sorry, this is G alpha. If you have an eigenspace with respect to root alpha, if you have another eigenspace with respect to root beta, then this is from Jacobi identity. Jacobi identity says that their bracket is in fact an element here. And it could be 0, but anyway. So the bracket is somehow related to sometimes sum of roots. Now, the roots, geometric roots, are kind of vectors. And here somehow vectors somehow makes perfect sense. Somehow vectors make sense, and that's kind of part of the rewrite. Another thing is maybe just one word of warning is that the number of kind of roots is actually 78, 133. Oh, sorry, so 72 and 128 or 6, I don't know. But if you count the number of vertices, actually it's less than that. So that means when you project from 6-dimensional space to this plane, actually some of the roots have multiplicities. So I think these two have multiplicities too. And also there are some of the vectors have multiplicities. So in this case, you can check that there are geometrically, so these two arcs, this arc and this arc, which are parallel and same as a vector, but they are different as geometric arc. So what I'm trying to say is that this notion of geometric arc is somehow better than just these vertices, because we can distinguish these two vectors, which are same as vectors, but not the same arc in the Miller fiber. So that is the subtlety which can be quite confusing here. But anyway, but the multiplicities can be handled very well in this Miller fiber model. All right, so sorry. So let me go to the definition. And so I'd like to say this is kind of a magic field. So this field classifies these geometric roots, all the roots, but it also classifies some kind of matrix factorizations. It also classifies indecomposable cube representations, and it classifies like roots of simple Lie algebras and so on. Classifies vanishing arcs. So this combinatorial gadget is a good tool for the classification problem. Okay, so let me quickly go to the definition of Lie bracket. So this H0 was the middle dimensional homology, and for each geometric root, we create some formal generator, one-dimensional formal generator. And for each geometric root, so this is an arc. For each arc, for bracket of arc with its orientation reversal is defined with a variation image of alpha. If we are in the homology of the Miller fiber, then bracket is defined to be 0. If from the closed curve to the arc, then this a bit complicated. Intersection number is the eigenvalue, or you can also substantially define it as variation of alpha intersection G of beta is this pairing, geometric pairing multiplied by G beta. And if you have two geometric arcs, then the bracket between them is the sum. If the sum is again a geometric root, and you have this sign given by intersection of its variation image of beta, intersection alpha. This geometry intersection over. And we can check that this actually defines desired simple Lie algebra of classical DCLE. So let me just briefly illustrate what happens for A2. So this middle dimensional homology is generated by H1, H2. These are closed curves, and these arcs are roots. So you can just compute and check it agrees with SL3 by hand. Sorry. In the case of AN, so this is like n gone, n plus 1 gone. So this E24, E25, E45, these are the elementary matrices like that, and the brackets just given by this concatenation of vectors in this case. So that's this bracket, you can think of it as geometrically like this. In the case of BN, it's SO2NC, and So they are given by this kind of arcs in this Miller fiber. And also, if you have a composition of two vectors which does not include this central puncture, then the bracket has usual sign. But if the triangle somehow contains this central puncture, then we need to put additional sign to the bracket. And that's, again, defines the simple Lie algebra isomorphic to SO2 and C. And for E6, it was similar game. So there are vectors and paper sums, and you can compute the Lie bracket by looking at the intersection numbers. Anyway, so let me stop here.
Are there any questions or comments?
One slide I saw is related to paper representation, and so how does it work?
So it says, so when you have this AD Dinkin diagram, AD figure, so given a Dinkin diagram, you can define, you can give the arrows directions, then this is the figure. And figure representation is like you assign a vector space and linear maps between the vector spaces. And then you look for like indecomposable representations. And the claim is that these arcs classify indecomposable figure representations. And the way I think about them is in the recently I defined flow homology arcs using this monodromy operation. So I defined some new. So here is the symplectic geometry, flow homology of monodromy. So when you have two arcs, I define this flow homology monodromy, and in fact, this is a graded vector space, and this you take the Euler pairing and you symmetrize it. This is the kind of the geometric bracket. So, but this geometric bracket, you don't need to know flow homology because it's kind of topological. You can just compute it. Anyway, so this lies behind. So in fact, I think of these arcs as generators of Fukaya category, and then so the simple roots it gives projective. Yeah, there is a kind of collection of roots which defines this, which corresponds to this Quiver algebra, and then if you look at endomorphism of that projective basis respect to another general arc is a Quiver representation. So from here, so just choose collection of object and look at form. Then this is a Quiver representation. Just home function is a Quiver representation. And then when does this gives indecomposables? It's exactly when these vanishing arcs or the roots.
Okay. So what does the monodromy player homology detect? Something?
So yes. So the reason I started studying this monodromy flow homology is the following. So when you have singularity, so people usually study this, for example, when you have like x to the n plus x cubed is y squared, then you perturb and you study this kind of vanishing cycles, right? And then you study this kind of collection of vanishing cycles here, right? So that's what you do. But somehow I wanted to define something which does not use this morphification. Maybe something which can be directly defined using this. So instead of this morphifying it, so we look at this monodromy rho. So this is this rho. and just use this one to define some certain flow homology. So that's so this defines certain flow homology theory. It's supposed to behave very similarly as in this case.
Are there something each application to mirror symmetry or
Yes, because the Fukaya side the theory of these vanishing cycles. This is called Fukaya side category, and this Fukaya side category is mirror to the Fano manifolds, Fano varieties. Yeah, so we define this, and so it's still not clear whether this is the same as Fukaya side category or this is more general. In the curve case, I think in higher dimensional case, this is more general than Fukaya side category, but the relation is even not yet very.
If I know there is also safer form in knot theory.
Safer form in knot theory.
So is there any relation between two safer forms?
So when you have this two variable singularity, so you have this singularity, then you get this kind of a sphere. Then at the boundary you get this knot. So this is a knot. In the case of like, if you have x cubed plus y squared, so this gives 2, 3 torus knot at the boundary. So I think they must be related to this. The last time I studied knot theory was like when I was at KAIST. 30 years ago.
Yeah. So I have a question. You mentioned at some point that you're proving a result about the Cox third element.
Oh yes,
Do you want to comment?
Yes, so then we can ask, because we know roots and so on, we can ask what is the Weil group action, right? So how does Weil group act? And so it turns out that Weil group action is actually not geometric, rather it's kind of combinatoric. So it's like reflection with respect to this arc is you take out this arc, you flip it and put it back. And what it means is all the arcs connected to this vertex, this arc will go here. And this arc will go here. So somehow this. Suppose you have this kind of all this kind of small bands, and you pick one and pick one. Anyway, so this reflection, this reflection in Weil group has some kind of combinatorial description, and then you can ask what is the Coxeter element. And Coxeter element is related to like for certain very special simple root corresponds to monodromy composed with orientation reversal. So here we know how monodromy acts. Monodromy is like you go to the opposite side and click on like this, and then so given an arc, you have an arc there, and you just take the monodromy orientation reversal of that arc. So that's how this Coxeter element acts, and you can check that it actually freely with n orbits, each orbit having this expected number of elements. Yes.
And for this, you need to choose a particular Coxeter element.
I think so.
So you need to
We chose
or the simple roots in a
simple we
in a
chose
certain way. Okay. Sure. And last question. Can you do you know if there's anything that can be done outside of simply raised type?
For the non-simply raised ones, as I told you, the non-simply raised ones are kind of invariant sub-algebras of simply raised ones. So, for example, when you have Dn, somehow you can fold and you get, I don't know which way, but you can fold it. Somehow this folding somehow is related to, you have these two parallel arcs. This arc and this arc, they are geometrically different but parallel. It turns out that if you consider the sum of these two as a generator, so instead of putting both of them as generators, you take the sum, only the sum as a generator, and look at the sub-algebra generated by this. It turns out to be this is exactly that. Yeah. So in all cases of this non-simply raised ones, Bn, Cn, therefore G2. So what you need to take average is in fact corresponds to all the parallel lines. It's somehow related to this multiplicity question on the Coxeter planes. Anyway, so.
Any other questions or comments? Okay, let's thank Professor Cheol-Hyun.